What's that? All right, so we were talking about. I do. So don't take it personal, is what you're saying? All right, so we're looking at where does your graphs change concavity? Right. No. All right, to the left of this x value, what would your function be? Concave up or down? To the left. It would be up, right? So f double prime of x would be greater than 0, and then to the left, or to the right, I mean, it would be less than 0. Okay? So right there at x equals p, this right here will be considered an inflection value. All right, now what about the third one? To the left, we have concave up. So the second derivative would be positive, and then to the right, second derivative would be negative. That's I'm sorry. That's positive, right? Because that's concave up. Okay, so do you have an inflection value at x equals p? No, right? Because there's no sign change from going concave up to down. Since we're both concave up to the left and to the right, you do not have an inflection value. So no inflection value at x equals p. No sign change. All right. Now to the left of x equals p, we are concave down, and then to the right we are concave up. However, what do we have there at x equals p? All right, so that means that this point here, in relationship to our original function, is what? If I have a vertical asymptote, that means my original function is what at that value? Right, I'm fine. So because this value is not in my original function, it cannot be considered a critical value because it's not in the domain. Right? So this is not in since x equals p is not in the domain. All right, so you have to make sure that you are seeing a sign change, and you have to make sure that they are also part of your original domain. All right, so a possible inflection value, we label that as PIV, is an x value in the domain of f of x such that the second derivative is equal to 0 or does not exist. So this is very similar to the first derivative when we were finding critical values. So they're really critical values for the second derivative. All right. F of x can change its concavity at either possible inflection value or discontinuity, like a vertical asymptote. And an inflection value can only occur at a possible inflection value, but not every possible inflection value is an inflection value. All right. That's kind of what we did for the last one. So, see, like this one's changing concavity, but this is not an inflection value because it's not in the domain. And like right here, your second derivative wouldn't exist. Your second derivative wouldn't exist there, but you're not seeing a sign change. All right, so when you guys are figuring out your intervals, you're going to need to come up with the second derivative, okay, where that equals 0 or does not exist, and you're going to use that number line chart again to figure out whether it's concave up or concave down. So if you get, right, so if it's positive, that means that it's concave up, and then if it's negative, it'll be concave down. All right. All right, so you have a function defined everywhere from a to k, is given below. So give possible inflection values. So this is where they might change concavity. So do we change concavity at letter A? No, right? What about B? B? All right, so you see how like we're getting closer to B, right? And this piece of the graph is what? Concave up or down? Down, right? And then as I get to B, after I get to B, what is it now? Concave up. So right at this value, what they're saying is this x value right here is where it changes from being concave down to concave up. So that would be considered a possible inflection value. Here? That's the first derivative, right? So the first derivative tells me that I'm increasing, and then to the left of this value, I would be decreasing. So now what you're trying to look for is where does your graph either like now lose water and then hold water. That's really what you're trying to look for now. So it's not always going to be like at the top of a peak or a valley. It's going to be, somewhere kind of in between. All right? And then once I get to C, right, I'm concave up, and then to the right of C, I am now concave down, right? So that's another possible inflection value. What about D? D would be. Right? And then what about E? Again, it's not, we're only asking for is it a possible. So this is where my second derivative is equal to 0 or it does not exist. So since you get that sharp turn, it is technically considered a possible inflection value. So that's where it might change concavity. What about H? Well, what is it to the left of H? Concave up. That would be up, and then to the right of H, it would be down, right? And then K is just a endpoint. Yeah. Right. I mean, it's still defined there, right? That's just a discontinuity, which you can change concavity at a discontinuity. So at E, if I were to do like F double prime of E, it would be does not exist. So that is technically a possible area where it could change concavity. But for this particular case, right, this would be concave up and then concave up, right? So the second derivative would be positive, second derivative would be positive. So this particular value is a possible inflection value, but once we do the next question, it's not like a definite inflection value. So for possibles, you're just trying to see, you know, where does it change concavity, where's the second derivative 0, or does not exist. So all these values that we have listed here are just possible inflection values. So if we had an equation and we were to do like the second derivative equal to 0 or does not exist, we would come up with these values. And then after we come up with these values, we want to test to see that we're seeing some type of sign change. So for the next part, at each possible inflection value, which we already came up with, determine if F has an inflection value at that point. So if I'm looking at B, right, to the left of B, I have second derivative would be negative, right? And then the second derivative to the right would be positive, right? So since I get that sign change going from negative to positive, x equals b is a inflection value. Right? So we get x equals b, concave down to concave up. What about C now? So we are concave up, and then once I get to C, I'm now what? All right, so C is another one. X equals C. Concave down. Oh, I'm sorry. Concave up to concave down. Now what about D? We have concave down, and then I am concave up. So there's another one. So x equals D, concave down to concave up. And then what about at E? So because you don't get that sign change, right, concave up to concave up, x equals E would not be an inflection value. So x equals E, not an inflection value. And then what about H? Right, okay. So concave down to concave up. Right, that's just a discontinuity. So you can get up to down. Sorry. So if that value wasn't there, then we won't be able to use it. So like, so we have this hole here, right? And if this value wasn't here, then because the function is not defined at that particular x value, then it wouldn't be an inflection value because it's not defined. Yeah, you do graphs. All right, so list the open intervals for which the graph is concave up, down, or constant. All right, so let's look for concave up. So where would your second derivative be positive? B to what? B to C. And where else? D to E. And then from E to E to H. Okay, good. And then it would be concave down from A to B, right? And then where else? C to D. And H to K. I don't think so. Right. But we have kind of curvatures all over the place, right? So, yeah, so it wouldn't be constant really anywhere. All right, so just like the first derivative number line chart can be used to determine support increasing and decreasing, second derivative can determine intervals for concavity as well as inflection points. So each of the following find the possible inflection values, the inflection values with justification, and then the open intervals of concavity. Okay. So we're only looking at it from 0 to 2 pi, right? We have sine of x, so that's continuous really everywhere. So we need to come up with the first derivative, right, which would be cosine of x. And then the second derivative would be negative sine of x, right? You're trying to see where does that equal 0. So where does sine of x equal 0 from 0 to 2 pi? So you would have what? Um, 0, pi, and 2 pi, right? So which ones actually can we get rid of, though? Right. So I can get rid of these two because I'm only looking at it from like a particular space, and I can't look to the left of 0 because that's not part of my interval, right? Because I just start at 0 and I end at 2 pi. So I'm not really concerned with to the left or to the right of that value or to the left of 0. Right, you don't really need to test them. So the only one I really want to look at is x equals pi. All right, so you got x f double prime. So we got pi. All right, so I'm going to test a little bit to the left and a little bit to the right. So I can do, say, pi over 2, and then 3 pi over 2. And again, you're plugging those values into your second derivative. So sine of pi over 2 would be what? 1, and then we got the negative on the outside, so that would be negative. And then if you do 3 pi over 2, sine of 3 pi over 2 is negative 1. And then you got the negative on the outside, so that makes it positive. All right? So what does that mean that I have at x equals pi if I get that sign change for the concave, and then we're looking for if it's an inflection value or not. So it's an inflection value because you get that sign change, right? And then to the left of pi, it would be concave down, and then to the right, it would be concave up. All right, so we got f of x has an inflection value at x equals pi, since f double prime goes from negative to positive at x equals pi. A lot of you guys on your quiz, you had some of this. A lot of you guys said, oh, f of x has a critical value at this point since it goes from negative to positive. You need to be very specific about what it is. Right? So you're not going to get points if you just leave it as it. All right? You need to label, okay, you know that this is your answer because the second derivative goes from negative to positive. Don't leave it as it. All right? All right, so we are concave down from 0 to pi, right? And then concave up from pi to 2 pi. Because that's kind of where it changes from being concave down to up, so you can leave it as an open interval wherever it changes. All right, so we got f of x is equal to 6 over x squared plus 3. Where would f of x be undefined? Is it a real number? That would be imaginary. Okay, so ignore that. Just trying to see, where does this equal 0? So if you set that equal to 0, right, you get x squared equals negative 3, which is then an imaginary number. So we're not really concerned with that. All right, so your first derivative would be negative 6 times x squared plus 3 to the negative 2 times 2x. All right, so that's what? Negative 12x times x squared plus 3 to the negative 2. Now, for the second derivative, we need to use what? Right. So you got one function, and you got I don't know. How is that a watermelon? That's purple. That's Alright, so you got negative 12 x squared plus 3 to the negative 2. And then I got, what else do I got? I got negative 12x. I got negative 2, so that's 24x times 2x, which would be 24x squared. No, 48x squared, sorry. 48x squared times x squared plus 3 to the negative 3. We can. So we can take out a negative 12 and an x squared plus 3 to the negative what? Negative 3, good. So I'm left with x squared plus 3. Right? So this times this will give you that. Right? Minus 4x squared. So I took out a negative 12, right? So then negative 12 times negative 4x squared will give you that 48x squared. All right, so if you simplify what's inside here, right, you got x squared minus 4x squared, so that's negative 3x squared. So you got negative 3x squared plus 3 over negative 12 times x squared plus 3 cubed. All right, so where does it equal 0? Is it 1? Plus or minus 1? So you got negative. Yeah, so x would be plus or minus 1. Does not exist anywhere? Okay, so we can get rid of that one. All right, so this is what we want to test. We have a possible inflection value at 1 and negative 1. So these are possible inflection value. All right, so we want to see, are they definite inflection values? All right, so if we plug in negative 2, what do you get? So this is always going to be positive. So negative, and then on top would be negative, positive. If I plug in 0, I get positive over a negative, which is negative, and then that would be a possible inflection value instead of a value to test. And if you plug in 2, you get negative 12. This is your second derivative right here. We're trying to see the sign change for the second derivative. So that would be what? Negative over a negative, which is positive. Okay, so we have a I know. -1 and +1. And then we are concave up from -infinity to -1 to 1 to infinity. And then concave down from -1 to 1. Now, what would your justification be for if you have an inflection value at -1? Tell me, what would you write? Perfect. And then maybe you guys can do math in English. Wouldn't that be fun? Well, that's good. Were you done with that? Or do you still need it? Just trying to save paper. All right, what do we do D for time purposes? All right, we have a polynomial, correct? So continuous everywhere. So we have 4x cubed minus 12x squared. Then you'd have to do product rule. So then you have 12x squared minus 24x. Where does that equal to 0? Now you can take out a 12x, and you're left with x minus 2. So x would be 0 and positive 2. Okay, so I'm going to test -1, 1, and 3. So if I do -1, that's negative, negative, positive. If I do 1, that's positive, negative, negative. 3 would be positive, positive. All right, so F has x equals 2, and we are concave up from -infinity to 0 and 2 to infinity. When you said that, you know that song, this is why I'm hot, or something like that? I got that, it's stuck in my, this is where it stops. This is where it stops. I don't know why it came to my head. This is why it stops. All right, we can do this one. Cube root of x, right? We could do it algebraically, or we can look at the graph. All right? So you have a... I know, we're kind of jumping around. All right, so you have a inflection value at what? Right? You don't always have to do it like that. If you have an idea of what the graph looks like, you can just graph it. So your concave up, your concave down, right there at 0. So x equals 0 is inflection value. And then you are concave up from negative infinity to 0, and then concave down from 0 to infinity. This is where we stop.